Okay, so the third influential system that Rick mentioned in the paper is BigTable from Google, which is a paper from 2006. And so here we're looking at primary index lookup, secondary index lookup. Transactions are also at the sort of scale of an individual record. Joins analytics is not supported by BigTable directly, but in in HBase, which is the open source implementation of it, and in Google's implementation as well, it was sort of designed to be compatible with MapReduce. And so you can run MapReduce over here over the same data that's stored in BigTable, so they're sort of complementary. And then there's some notion of integrity constraints or schema here, and we'll talk a little bit about how that's implemented. There's no views that I can see, and there's no sort of language level or algebra level for manipulating these things. They're all sort of NoSQL style micro interactions with individual records and cells. Okay. So this is a paper in OSDI from 2006 and some overlap with the authors of the MapReduce paper, and it was sort of designed from the start to be complementary of MapReduce. So if you can remember, what was one of the main things that was missing from MapReduce, or maybe a few things that were missing? Well, in particular, you couldn't look things up by index. You couldn't get these little sort of low latency accesses. And so, for example, if you wanted to find all the records, given a big data set, you want to find all the records in some other data set that correspond to it. You want to do some sort of a join. The best you could do is process. You had to touch every single record. There was no way to zoom in to just the right ones you wanted. Okay. And so BigTable provides that fast key-based lookup, but you can still process the overall data as a big set of key value records with MapReduce. Fine. So the data model here is a sparse, distributed, persistent, multidimensional sorted map. And what they mean here is that you can basically access any cell in a big table by giving a row ID, a column name, and a timestamp. Timestamp isn't really described in this English description here. It's for versioning. So when after you have updates, you'll keep track of past versions of the same cell. Okay, and so if you provide these three parameters, BigTable will return you a string quickly. All right. So each row is data is all sorted lexicographically by the row key, which is this row ID in this bit, right? So this is some sort of primary key in sort of relational language, or just a key in kind of a NoSQL framework. And then this key range, I say that they're integers, then contiguous subranges of this set of keys will be assigned to a tablet. Right? Okay, so this is a little different way of dividing up the data than we've seen in the past in at least one system. We talked about a parallel database model, and we happen to use the example from Teradata. And so how did they break up data? Well, they did it by hashing, right? So every individual record would be sent to a server according to a hash function, which you can generally just think of as sort of round robin. The point is that two keys that are next to each other in space, so sort of timestamp 5 p.m. and timestamp 5:01, there's no reason to believe that 5 o'clock and 5:01 are going to be on the same server in Teradata's model. Here they are. So what are the pros and cons with this? Well, if you're going to typically access a whole range of keys at once, it's pretty nice to be able to, when you get one, you get the others too, sort of for free, because you're pulling them all back. However, if one particular key range is much more popular than the others, just by using the time example again, the most recent data perhaps is the most popular. And so if all the requests are going to that one key range, then you've got a bunch of idle servers hosting all the other tablets that are corresponding to older times, and all the requests are going to this one tablet. And so for that reason, Teradata sort of chooses to hash everything, so that on every request, all the servers may have to be accessed, but that's good for scalability. Okay. So pros and cons. All right, so the tablet here is the unit of distribution and load balancing. So they'll move tablets between servers as things start to get unbalanced, right? If your key range is, January, February, March, April, May, and there's a whole lot of data coming in for March, they'll split that into multiple tablets and start moving those tablets around between servers in order to balance things. Okay. So within a single table, you can have these groups of columns called column families, and the column names have the family right in there as a qualifier. And this family is the basic unit of access control, so you can provide permissions on a group of columns. Memory accounting, in that they're sort of allocated as a unit in memory, and then disk accounting, so they're moved around on disk as a unit as well. Okay, and so they make this point that typically all columns in a family are the same type, which I find a little unusual because they sort of talk about it being the basic unit of access control, which suggests that there's things that go together for access control, sort of social security number and employee ID or something, may or may not be the same type. So there's sort of a logical grouping requirement that they seem to be trying to meet, but then they're the same type. They have to be the same type, which is for a very technical reason, specifically because they want to compress these things. So if you have a whole bunch of integers, it's easier to compress than if you have a mix of integers and strings. Okay, so I think they're trying to kill too many birds with one stone here. All right, and then each cell can be versioned, which is the third part of that key lookup, right? Row ID, column name, and timestamp. And each new version increments that timestamp. And so here you can enact different kinds of policies where you only keep the latest in versions, or you keep only the versions since a given timestamp. Fine. So how these tablets are managed is a master will assign the tablets to tablet servers, and the tablet server handles reads and writes from the tablets it controls. Okay, and so clients communicate directly with the tablet server as opposed to having to go through the master every time, which helps with scalability. Okay, and then when a tablet starts to get too big, it'll split it and load balance it. All right. So the metadata keeping track of where tablets are located is organized itself in another tablet. So there's a root tablet here that describes each record in here describes a group of records, a group of location records in a bigger table. And then each one of these metadata tablets gives the location of a particular user table. Okay. And so this is how you sort of keep track hierarchically of where everything is at one time. And so Chubby, that they mention in the paper, is a distributed lock service for controlling access to these things. And I'm not going to talk too much about it. Okay, so how are reads and writes handled in this system? Well, there's a table in memory that stores a sequence of updates as they occur. Okay, and a write operation adds a record into the memory resident table, but it's also written to a log for fault tolerance purposes. Okay, so if this server goes down, it reads the tablet log and can reconstruct what's going on. And then read operations are served by reading these SS table files, the actual data itself, but then also by applying the updates from the mem table on the fly. Right? So it needs a stream. It says here's the value, and then here's the stream of updates I need to apply to the value to get the true value. Okay, and then there's two. So this is fine, but what happens when the mem table gets bigger and bigger and bigger? Well, there's two types of events that occur to do the bookkeeping here. So one is a minor compaction, and this is when the mem table gets big, it gets written out into a new SS table file, and the changes are merged. Okay, and then a major compaction is take all the SS tables and rewrite them all into one big one that may be split into multiple files, and also clean up any deletes that have occurred. So deletes are just appended as instructions, but it doesn't actually remove anything, so they're sort of garbage collected. Okay, and so this way you can keep sort of the read throughput pretty high and sort of keep this upkeep going on in the background. All right, so there's a host of other tricks here too, where they can do various forms of compression specified by which can be specified by the clients. There's some different ways of doing it. They use Bloom filters to speed up existence tests. So if I give you a row ID, a column ID, and a timestamp, and say, find me this value, what these Bloom filters allow you to do is to very quickly determine whether that does not exist in the system. So these Bloom filter data structures are pretty cool, and I'm going to walk through them in this course in a couple of weeks. Okay, so they help you quickly determine whether that key does not exist in the system and avoids disk accesses during reads. All right. And then there's locality groups you can define, which is another layer of organization on top of families. And these are groups of column families that tend to be accessed together. Fine. And then another trick here is to make sure that the SS tables, these disk chunks, are actually immutable. They never get written directly. The only time they get written is when these major compactions happen and the whole thing is sort of reorganized. And so that means that the only writable data structure is this mem table. And so the amount of concurrency control to keep things down, it remains pretty simple.